Thanks again for your kind introduction and for the opportunity to celebrate Jim Anderson with our prize. I want to thank the Chemistry and Chemical Biology Department for hosting today, and all of you in attendance for joining us in celebrating Jim and his accomplishments, and of course to the Dreyfus team that made all this possible. So thank you very much. The 2021 Dreyfus Prize is awarded to Jim for advances in environmental chemistry. This is the 7th distinct Dreyfus Prize we've done, which is awarded every 2 years. The prior award was to Robert Langer in 2019. Our inaugural award was to George Whitesides, who's here in the audience right over here. So, George. And the next award is in imaging. So be sure to send in your applications for imaging in the chemical sciences. Let's see. So back to the 2021 award. Jim is receiving this award for decades of landmark contributions to the field of environmental chemistry. He's honored for pioneering measurements of the free radicals that drive the chemistry of the atmosphere, establishing the path to worldwide agreements to protect the stratospheric ozone layer. His work and advocacy have had an enduring impact on scientists, policymakers, students, and society. Now, Jim's connection to the foundation goes back to 1994, where he helped us develop a program in postdoctoral research in environmental sciences, and where we have awarded over 170 postdoctoral and professorial teams in that research. Jim has been a steadfast supporter of the foundation and a personal friend and mentor to me and my family. 75 years ago, Camille Dreyfus had the following idea in founding the foundation: to advance the science of chemistry, chemical engineering, and related sciences as a means of improving human relations and circumstances throughout the world. I'm sure the Dreyfus brothers would be very proud of the selection of Jim Anderson for the 2021 Dreyfus Prize. Congratulations, Jim. Come on up. I'm going to read the citation. This is awarded to James G. Anderson for pioneering measurements of the free radicals that drive the chemistry of the atmosphere, establishing the foundation for worldwide agreements to protect the stratospheric ozone layer, from the Camille and Henry Dreyfus Foundation. Congratulations. You can keep that, and you get this, too. Ready? I guess so. Ooh, that's hefty. You got to wear it the rest of the day. There we go. Congratulations, Jim. Thank you. I'm going to call up Milan, who's going to introduce you. Thank you, Jim. I'm going to ask Milan Mrsic, my co-director of the foundation, to come up and say a few words of introduction to Jim's remarks.
Do you want to give me the mic?
Oh, yes.
Don't go too far, Jim. That's terrific. Thank you, Scott. And I'd also, on behalf of the Board of Directors of the Dreyfus Foundation, like to welcome everybody to today's celebration. And it's a real delight, a real pleasure to introduce Professor Jim Anderson, the Philip Weld Professor of Atmospheric Chemistry in the Department of Chemistry and Chemical Biology here at Harvard, as the Dreyfus Prize awardee this year. Jim is a scientist who's dedicated his life and career to the study of chemistry of Earth's atmosphere and its climate. Jim has created an entire field of study of highly complex reaction processes, notably with respect to the stratospheric ozone. And he's distinguished himself as a pioneering scholar, an impactful policy advocate, and an innovative teacher. Jim was always drawn to challenging problems and questions, and he certainly found his calling in the chemistry of atmospheric processes. The study of radicals, even under ideal laboratory conditions, is highly and exceedingly difficult. Jim developed methods for detecting radicals with remarkable sensitivity at levels of 1 part in 10 to the 14th. His laboratory has had a substantial engineering effort to develop the instrumentation that can be used and is required for those measurements. And he's applied those to really rigorous and field-changing kinetic studies of these complex processes. And from those, has gleaned much mechanistic insight that's remarkably let our understanding evolve from the molecular to the atmospheric and climate systems. And perhaps even more remarkably, Jim and his team have built instrumentation that doesn't operate in the laboratory, but on aircraft to make these measurements in the atmosphere. Professor Anderson is certainly most recognized for his pioneering in situ measurement of radicals that explain ozone hole chemistry dynamics. In the early 1970s, it was postulated that chlorofluorocarbons in the atmosphere would contribute to ozone degradation. And it was a hypothesis that you can imagine was hotly contested by the industry that had interests in these business products. And they cited a lack of data and a lack of evidence. Well, Jim's team performed the first measurements of halogen radicals that derived from the breakdown of chlorofluorocarbons, including chlorine and chlorine monoxide. And he conducted pivotal field studies in the atmosphere that conclusively demonstrated that the halogen radicals were the cause of the ozone hole. This work was widely referred to as the smoking gun in the ozone problem. And it's found many homes and undergraduate texts where students learn about these basic radical processes. Well, those results, together with Jim's very effective testimony at House and Senate hearings and his presence in the media as a science educator, were critical in leading to the United Nations passing and revising the Montreal Protocols, a set of rules that were widely adopted to either ramp down or fully eliminate many of the chemicals that are responsible for ozone degradation. You know, there are really few examples where really fundamental chemical studies can have such a sweeping societal impact. And Jim stands alone among those in being a leader both in the science, the chemistry, and also in the policy advocacy position. I also want to comment about the education side because Jim's also been very passionate about undergraduate education. And he spent a number of years here at Harvard reformatting the introductory chemical sequence and really presenting the same important basic concepts, but doing it in the context of technology, global energy, and climate. And I didn't know we'd have props, Jim, but Jim has also just had published his new textbook, which is super. I spent an evening looking through it and reading sections, and you know, this is really going to appeal to undergraduates and give them a reason to be interested in chemistry and a real satisfaction in understanding the principles. And now that it's in a book, many will benefit from that.
But that wasn't bedtime reading.
Well, for me, it's always hard to say, but but I do want to tell one story. One I wouldn't be proper to share, but one is. And that is, you know, Jim's passion for undergraduates and these young students. He was an early adopter of electric vehicles, and he was so excited about these, he wanted the students in his class to experience them. So he had the street closed off and sat in the car demonstrating little regard for his personal assets, but sat in the car while students had a chance to drive the electric vehicle. I think that's terrific.
And thanks to my wife, she allowed this.
Well, let me, briefly also say that, this record of spanning precise analytical measurements in the laboratory, airborne field studies, policy initiatives both at the national and international stages, and a reimagining of the chemistry curriculum for undergraduate students is remarkable if you looked at any one, but to have all three of those passions and records of success in one person is truly remarkable. It's certainly been recognized by a number of really prestigious prizes. I know they're in the pamphlet that you have, so I won't reread them now, Jim. But we just want to say we couldn't be more delighted to have you as the Dreyfus Prize recipient, and we know that your legacy will last for many generations. So thank you.
Well, thank you very much for coming. My final sentence in this presentation would be a profound thanks to the colleagues that I have at this university and elsewhere, but primarily my colleagues here at Harvard over the 150 years that I've been here have been a profound contribution to my happiness, my creativity, my well-being, and this spans research areas, but also teaching. And so I have to say thank you, and the most important thing to me is the wonderful relationship that exists at this university and the way the faculty gets along with one another. It's a huge contribution. Okay, so today I'm going to wander around because that's what I like to do. But I also have to say, I just had my left knee replaced, so the limp is something you don't need to worry about. It'll pass. So, first of all, thank you very much for the kind introduction by all of you. And President Bacow, it's true, we share this passion that I didn't think you would ever admit in public, but now that it's out, I want to underline the fact that it indeed is something to share and treasure. The Dreyfus Foundation statement of purpose is remarkable when you look back 76 years to its origin, because the insight that went into it, I think, was reflected in the individuals who carried this forward in time, in particular to advance the science of chemistry, chemical engineering, and related sciences as a means of improving human relations and circumstances throughout the world. And I put in now more than ever, because I think part of the subplot of what I'm going to present is that things are becoming far more complicated, far faster than we're solving them. And that's a fundamental principle that is of great concern to me. But the insight that went into defining that as a guiding principle, of course, was ultimately reflected in the selection of people to carry it out. And the origin, of course, started with these two brothers working on the creation of new products and new materials, and the close relationship between the two of them. And the memorial to both men, when Camille died in '56, joined Henry with him to take the lead in identifying and addressing needs and opportunities in the chemical sciences. And the way in which the core leadership of the Dreyfus Foundation has carried this vision forward is truly a benchmark. And if you look at the influence that the Dreyfus Foundation has had on education, the range is remarkable. Of course, the Teacher Scholar Awards are probably Exhibit A over the full length and breadth of this. These dynamic postdoctoral programs, they're created with a set life span so that they move on to new and different areas as areas become more relevant, more serious, and more complicated. Lectureships, new faculty awards, postdoctoral fellowships in liberal arts colleges. It's this balance, not just looking at research universities, but looking across the full spectrum of undergraduate education. The postdoctoral fellowships are in combination with scholar fellow programs, chemistry short film series, ACS awards encouraging women into careers in chemistry. This is all a reflection of the sensitivity of breadth and depth that the Dreyfus Foundation brings to all of us. And so now I'm going to turn to something that George Whitesides taught me. And George Whitesides has taught me a lot of things. And the way in which he brought a culture to this Dreyfus Prize I found remarkable, because he examined the evolution of scientific strategy by looking at very early influence, benchmarks, the early influence on perspectives that students see as they're coming up through high school and college, but also the unpredictability of unfolding events. This is going to be a central part of what I discuss, because almost everything I've ever worked on was unpredictable. Sometimes unpredictable before I worked on it, sometimes afterwards, but always unpredictable. And the influence of key individuals. This is something that, reflecting back on this, I'm going to mention a number of examples. But probably the most important of this are the undergraduate students, graduate students, and postdocs that I've worked with, because it's very critical to underline the fact that everything I'm going to talk about was done by my postdocs, my graduate students, my undergraduate students, and the integral of science and engineering within my research group. So I want to make sure that that's emphasized right from the beginning. The evolution of the emerging focus of research strategy, how do all these factors feed into that? And then driving to the future, undergraduates, graduate students, and postdocs. That connection is what George set out in his inaugural discussion of this, and I couldn't be more appreciative. So, I'm going to show pictures of the evolving research groups through the years. Some are on the front stairs of various buildings, because we've been here long enough to occupy multiple buildings. Some of them involve going to the Arctic, to the Antarctic, but the core and the backbone of this resides within the wonderful members of the group. And I could sit here and show this for the next 20 minutes, but I want to bring these up again. So back to the primary approach here. Early influence. This is a picture that embodies early influence, because I grew up in a house belonging to my father and mother, and my father worked on radar in the South Pacific during the Second World War. And as a result, the basement of the house was filled with drill presses, band saws, tools, dark rooms. The entire first floor of the house was a machine shop. I took it for granted, but when I look back, living in the midst of all of that machinery and just deciding the first thing in the morning the key problem was, what am I going to build today? I didn't take that seriously until, I sort of rethought it. But it came down to fixing things, motors in particular, and here I am going after a 2.5 horsepower Johnson outboard that wasn't running, but figuring out why at the moment wasn't so important. But when I look back on the pattern, it turns out that it was. Here's another example, building airplanes. We're going to be talking about airplanes today. This is the first grade, and I'm building this gasoline-powered aircraft, and I built many of these in that same basement. But it had a huge effect in the longer term, and then that gave way to boats, building boats, bigger and bigger boats, repairing automobiles that I was primarily responsible for destroying. All of these things, it was a matter of, well, if something bad happened, don't worry about it, just fix it. Another lesson. Then this influence, the Cold War, and what that did to students, because I entered college in the 60s, and so Pullman, Washington, I don't blame anybody for not knowing where it is. It's in eastern Washington. And we used to go under our desks twice a week, hiding from nuclear attack. Now, Pullman, Washington has to be the last target anybody would ever suggest for this. But that didn't stop twice a week diving under the desk to avoid these attacks. Well, the influence of the Cold War was interesting because as I came out of high school, I came away with the feeling that if I didn't understand physics, I couldn't possibly be proactive in the solution to this problem, because obviously physics was at the base of it. And so that actually had a great deal to do with all of the things that came thereafter. And I have to say, in the fall of my freshman year, I started with, there were 5 levels of physics courses for freshmen. I started with 330 physics concentrators, and 19 of us finished. And at the moment that I finished, I thought, well, I'm fairly proud of myself. It didn't take me more than a year or two to realize how disgusting that was, because I was still friends with a lot of those original 330, and that system eliminated far more creativity from physics than it ever kept in that final 19. And so this was an essential part of how I began to think about restructuring undergraduate education, which would take years to evolve, but it was that influence of the First World of the Cold War that was so important. Now, space physics became very interesting to me, in particular the radio astronomy of Io, the moon of Jupiter. I got really enthralled with this late in my senior year and went to the High Altitude Observatory in Boulder, Colorado to study this. The epitome of unfolding, unpredictable events then occurred because I went through the standard courses in the freshman year. They're just, E&M, quantum, and so on. But at the end of the first year, I was broke. I had an NSF fellowship. It paid $200 a month, and I couldn't quite make that last 12th month. So I went in to see Charles Barth, who was the director of the Space Physics Lab in Boulder. He was sending probes to Mars and Venus and so on. And so I went in and I thought I'd ask him for a letter of recommendation. And these letters of recommendation have become extremely important to me. I write about 70 of them a year for students here because this was so important to me, and it was taught to me by this single event. And this is a picture of Charlie Barth sending probes to Venus and Mars, but he also was coupled to Ball Aerospace Systems. So I figured I'll go in and ask him for a letter of recommendation to work at Ball Brothers for a month. So I went in and we spoke briefly, and he looked at me and he said, Ball Brothers has a 3-week gestation period for new employees. Do you think they're going to hire you for 4 weeks? I said, oh, God, okay. He said, I've got a lab upstairs. I'll hire you for a month, and we won't even worry about it. Well, Barth was looking at free radicals as they controlled international communications funded by the Cold War. But what was remarkable was that I worked for the month in his lab, but then decided this was so interesting, I didn't believe it, and 2 or 3 months later, I took an exam before you could do research. All of us know about that. And about a week after I took that exam, I looked in my mailbox, and here were 2 NASA rocket contracts. And I thought, this has been misfiled, so this is about $1 million worth of research. So I went into Barth's office. I said, I'm sorry these were misfiled. And they said, no, they weren't. Those are for you to do with what you wish. Two rocket contracts, including all of the instrument design, build from scratch. That is unusual, and that led to virtually everything that followed, because I ended up building an instrument which could measure the hydroxyl radical OH in the atmosphere for the first time. But I had to build that instrument from scratch, and so all of a sudden the way in which that's done became a critical part of the approach. And so immediately, it wasn't just a matter of designing the instrument for the nose, and I borrowed this from David Wilmoth. This is a modern flow system, but I immediately had to use flow systems to start to look at the hydroxyl radical, because I had to create it in order to detect it, in order to set up the instrument properly. But it was the development of the necessity for creating the OH radical in known amounts that began to move the center of gravity over toward the laboratory aspects. And this is Herb Broida. Many of you, some of you in the audience know him. He was a leading union between physics and chemistry for many, many years, and he happened to be doing a sabbatical on my second year of graduate school. So we became fast friends working on this. He was showing me how to do laboratory experiments in ways that I've never seen anybody do them since. And this brought back this whole focus then on how you develop the ability to look at these free radicals. And this particular reaction has importance because OH plus ozone is one of the central reactions in all of photochemistry, and yet its rate had never been measured. Also, this era, in the early 70s, the world has never been the same since Hal Johnston entered into it. And this is a famous story that occurred at MIT, where there was a huge federal report that said, no, the effluents from aircraft will not affect ozone, nor will anything else. And Hal happened to be invited to that presentation. And the only thing that report left out was catalysis, catalytic reactions. And Hal was so enraged by the stupidity of this report that he literally carved a hole in the stratosphere. He just exploded in public. And those of you, many of you know him, he's the most gentle, thoughtful, but he literally flew into a rage in public over this. And that reshaped the entire federal research structure overnight, because any committee that is put together to study free radical reactions that doesn't understand catalysis shouldn't be there. And so this new era was born, and of course, Hal pointed out that the oxides of nitrogen coming out of the exhaust of aircraft would trigger this two-step process, reforming the O2 bond, but leaving NO and NO2 unaffected, which, of course, it's catalytic. So one NO2 molecule can destroy millions of ozone molecules. That's no problem at all. And so that completely reset the whole concept of how the atmosphere works, but also how you address problems in the laboratory. Namely, you need to know the rates of each one of these steps in order to analyze it quantitatively. Well, I was interested in studying OH, and I had just arrived in Fred Kaufman's lab at the University of Pittsburgh I was hired into the physics department, but I actually wanted to work in chemistry because chemistry free radicals was starting to get really exciting. And so just for all of you to represent how the first day at work can be the worst, this was an example. So Tom Donahue in the physics department had actually offered me the position, but he and Fred Kaufman and I went to lunch together. I had never met Fred. He has, and still is, famous for terrifying people, unless you're working with him and then he's a teddy bear, but he terrifies people. So we're walking to lunch and he's going on and on about Paul Crutzen, not knowing anything about kinetics because Paul in his model had used OH plus O3, which Fred had published as an upper limit, not as a measured reaction rate constant. And so Fred was just going on and on about how the fact that modelers don't understand anything about molecular reactions or anything else. And the only problem was that in my thesis I had done a model and I had used exactly the same expression for OH plus ozone. So I'm sitting there watching croutons float around in my soup at lunch saying, well, am I going to fess up here? And I decided, yes, I am. So I said, well, I'm sorry to report that I did a model in my just completed thesis, and I used that same upper limit as a measured reaction rate constant. And Fred just went, oh, God, he rolled his eyes. He looked at Tom Donahue like, where did you find this guy? I mean, can't we just end lunch and get on with this? Well, then I made my second mistake, and I said, well, why hasn't OH plus ozone been measured? And Fred rolls his eyes again. He looks over at Tom. He goes, oh, God. Anybody knows that OH reacts with itself so fast you can't see it react with anything else unless you get its concentration low enough. And so I said, well, I think I can measure OH low enough to get rid of its disproportionation. And Fred rolled his eyes again. Tom said, okay, well, when you start working in a couple of weeks, I'll pay for the system to build it to see if this works. And so the result was that Fred and I chewed through free radical kinetics for the next 2.5 years. We measured, along with colleagues, 15 to 20 of these key reaction rate constants, because once you know how to measure OH low enough, you can get rid of this reaction and everything else becomes simple. Okay, then the question becomes, well, what about these radicals in the stratosphere? Well, so astrophysics had developed these balloon systems, which they're 40 million cubic feet in volume. They would fit into Harvard Stadium just as an egg into an egg cup. They're that big. They get to 40-kilometer altitude. And that is the way in which we can reach the stratosphere to make these measurements. But the OH concentration is a part in 10 to the 14, as was mentioned. So developing an optical system that could do that was the next challenge. And so these instruments now took on the look of a nacelle, and they're lofted at the top of the stratosphere and dropped on a parachute. So the flow through this instrument starts almost supersonic at the top of the stratosphere and slows down as the parachute comes down. But it demonstrated that you could, in fact, measure free radicals in situ. And here's a picture taken by NASA of the first flight coming back down. They were photographing astronauts. That's the only reason they happened to take a picture of a science experiment. Next was the introduction of chlorine in 1994, and this is Ralph Cicerone. Cicerone and Szélarski introduced the potential importance of chlorine because it's an effluent of the space shuttle, and that all of a sudden released resources from NASA to find out about this. And at the same time, Mario Molina and Sherry Rowland introduced the idea of chlorine coming from CFCs. And the way in which this was reacted to was alluded to a couple of times already. That is, there was huge blowback from DuPont. I mean, DuPont went after proponents of this viciously. I had never understood, and of course we see this all the time today, but this was a very difficult time. And the next introduction was bromine. Mike McElroy, Steve Wolfsey, brought bromine into the picture from halons, which was an extremely important contribution because ozone catalytic loss goes as a square of the CLO concentration, but linearly with BRO. And so at intermediate CLO concentrations, it's a combination of chlorine and bromine. So the objective then is a quantitative determination of the mechanisms controlling the concentrations. And this gets back to a fundamental principle in the physical sciences, that if you're going to understand the coupled mechanisms that control a system, particularly the control of a system that's being forced externally, you have to have simultaneous observations of the coupled variables with high spatial resolution simultaneously determined within the same volume elements. You have to understand that quantitative coupling, or for the mathematicians in the room, you have to experimentally determine the Jacobians that are related. Otherwise, you cannot define the physics, the chemistry, the biology, and how that's going to respond to external forcing. So these high spatial resolution, temporally resolved three-dimensional measurements within the same volume element are an observational objective that you cannot compromise. And so what do? Well, we build a observing system for every single one of these radicals, and we just add them to the payload. We're still dropping this at 40 kilometers, even though it now weighs 5,000 pounds. Each one of these cells is a different free radical measurement. They land less than elegantly most of the time, but they are recovered, repaired, returned to the laboratory. But I should point out that each one of these flow systems that measures the free radical comes back to the laboratory, and it fits into the laboratory system. So it's fed the same free radical under the same pressure conditions, and the connectivity between the laboratory calibration and the in-flight was dramatically simplified that way, and so there was no argument about it. And so this is the research group that transitioned from the late 78 into early 80s when we started doing these measurements. The next issue involved the quality of the observations, and when those instruments were dropped at 40 kilometers, reaching almost supersonic speeds, that made kinetics very difficult. What would be much better would be to have a controlled descent where the descent of the instrument was controlled and repetitive. And so that led to the idea of building a reel-down system, which has a winch in it with 15 kilometers of Kevlar, which is extremely strong material, that would allow the lowering of that instrument through the full 15 kilometers that are critical in the stratosphere, drawing it back up and then redoing the measurement, but at low velocity so you could control it. And so that's what led then to the use of these balloons and the determination of these rate-limiting radicals. And so this system looks hanging from what's called Tiny Tim, with the balloon off to the left-hand side. This negotiates under the balloon as it comes up over the top and picks up the tension and then lifts the payload off. And so when this is released onto the balloon, it then ascends to 40 kilometers. But what's interesting, and when we submitted this proposal, NASA, along with everybody else, said, that's ridiculous. The stratosphere is going to tear it apart. It's hopeless. It's a stupid idea, which is a summary of the response I get from every single proposal I ever send in. And remarkably, a number of people, and George started this, I don't want to keep picking on you, but you mentioned that the greatest impediment to innovation was the peer review process. And I can tell you, I completely concur with that. There's not a single thing I've ever done that hasn't been rejected multiple times. And it's compounded by the fact that government bureaucracy tends to end up with programs, and if something you are thinking about isn't in the program, it doesn't even get past the mailroom. So this is a real problem because this was called ridiculous, hopeless, all the rest of the adjectives. But somehow somebody made a mistake and cleared this grant before it was blocked. So we actually built it, flew it, and this is looking down at the payload. This is a parachute you see on the left, and the payload is hanging. Now it's dropping, and it's going down at 10 meters a second, but it's going down for 15 kilometers. And there's a little Kevlar filament connecting this instrument. But the upshot was that the instrument is as stable as a block of metal lowered into a slowly flowing stream. It's completely stable. And you notice, you see this little streak here? That's the sun shining off the Kevlar filament, which is only 1/8 of an inch in diameter. But it'll come reeling back up and position itself, and then we could re-lower it. And that dramatically improved the quality. Okay, so then, now Walter Sullivan, yeah, good. I appreciate your sense of humor, because that was exactly how I reacted. Walter Sullivan, as many of you know, was sort of the lead writer for the New York Times at the time. He says, world's biggest yo-yo may settle ozone layer debate. And all of my friends wrote to me immediately, said, well, the New York Times doesn't always get it right, but this time they did. So I'd write back and say, thank you very much. Anyway, so what happened next? Okay, so this, now we're looking at 1984-ish, but then 1986 came along, and the most stunning revelation in all of atmospheric sciences came out 10 years after it should have. And that is in 86, the British Antarctic Survey, they discovered the Antarctic ozone hole. And they discovered it by sitting on the ground in the Antarctic and looking at 2537, the absorption of ozone, as the sun came up day after day, as winter evolved into spring, into summer. And the total ozone column, these are in Dobson units, we don't worry about it, it's a ratio that matters. So through the fullness of the time of evolution of species on the planet, the total ozone was about 320, 330 Dobson units. And that was true out to about 1975, 76. And all of a sudden it plunged, and it plunged every single spring. And yet, this is out of Cambridge, and yet they didn't publish it until 1986. This is a 30% decrease in ozone column. And by the way, we know, and already by that time, the sensitivity of humans to UV, because of course UV radiation breaks the base pair across a double helix of DNA, but just a 1, 2, 3, 4, 5% reduction in ozone column has a huge impact on public health. And so this, of course, put the global community into a state of panic because there was no description. And we're used to seeing these satellite observations that map out the same Dobson units in color, showing this huge absence of ozone over the, or lowering of ozone over the Antarctic. But it was actually not ozone, it was not satellites that discovered this. And the reason satellites didn't discover it was that they had one if statement in the graphical representation that said, if the ozone concentration is below, say, 300 or 290 Dobson units, insert the climatological mean. So they obviated their ability to, on that simple if statement, to actually discover the Antarctic ozone hole. Okay, so then of course the question was, well, what's causing this massive loss? And so there were three categories of theses. One is high energy particles coming in from the sun and breaking the N2O2 bonds to create the oxides of nitrogen, following Hal Johnson's suggestion of the supersonic aircraft. Then the dynamical explanation, which said, well, as the sun comes into the southern hemisphere, it warms the air, and that carries ozone-rich air out to mid-latitudes. And then the third category was that it was a chemical result of the presence of chlorine, CFCs, that then broke down to form the rate-limiting chlorine radicals, and also halons for bromine. So that brought a whole new venue to our laboratory. We needed to fly into the stratosphere, but we needed to do horizontal scans to diagnose this problem. And so this is the NASA ER-2, which is essentially a U-2 spy plane. It can fly to 75,000 feet, fly into the stratosphere, but it also required an entirely new architecture for the instrumentation, because rather than falling vertically at 10 meters a second, we had to fly horizontally at 200 meters a second. And so that required a new fluid dynamical study along with the rest of the development. But that also evolved. We had 6-7 months to build this from scratch before the next spring term. And here's Joe DeMuse and Bill Brune working on this new instrument design with no time at all to get it ready. But the flight of that followed the following pattern. So we were stationed at Punta Arenas, Chile, right here. The U-2 would take off, and it literally flies almost vertically into the stratosphere. And then it flies horizontally into the Antarctic vortex. And of course, the Arctic vortex is now famous. But its basic physics is that as air cools in the core of the winter, air moves in from higher latitudes, but the Coriolis force in the southern hemisphere turns it to the left, and it creates this gyre. But that gyre isolates the core from the rest of the global atmosphere. So what we're essentially delivered is a beaker, chemical beaker, sitting over the Antarctic continent, the walls through which we can fly the aircraft, because it's conservation of angular momentum that actually blocks any interchange across this vortex edge. And you can see the vortex edge is here. But in late August, the sun is just coming up over the horizon at this latitude in the southern hemisphere, and ozone is emerging largely unscathed through the winter. The CLO radical, extracted from chlorofluorocarbons, is jumping from a few tens of parts per trillion up to almost 1,000 parts per trillion. But the key thing is, that's an initial condition. 3 weeks later, 16th of September, now there's this dramatic anti-correlation between the rate-limiting radical and the ozone concentration. And so it was that combination of circumstances that allowed the unequivocal nature of the scientific conclusions to evolve. Because when we started to testify in front of the House and the Senate, this description that shows the anti-correlation of that radical with the ozone concentration was what was the compelling presentation. It didn't involve all of the details of chemical kinetics and spectroscopy or anything else. It was a clear picture. But the chemists, and by the way, I've got a picture of Norton Allen here, who joined us from Harvard commencement right out of college and transformed our entire software systems. But he and I were staring at the screen in Punta Arenas, Chile, when he pulled the ozone CLO combination up, and we both looked at it, and we looked at each other, and we knew that life would never be the same again. And Norton has written every single line of every single algorithm we've ever flown, and continues to do so. And it's one of these times when you remember exactly what the room looked like, who was there. Okay, but here's the point. From the chemistry community point of view, I said, okay, that's a really neat picture. How does the rate-limiting step in the catalytic cycle compare with the observed rate of ozone loss inside of this beaker? And this is the beautiful thing about catalytic processes. They're a series of reactions, but the rate is set by the slowest of all of them. And in this case, the slowest one is CLO plus CLO forming the dimer. This was the Molina mechanism, the genius mechanism actually. It had never been put up before. This is like hydrogen peroxide, but except with chlorine, and it's bound such that when a UV photon breaks the bond, it doesn't break the weak OO bond, it breaks the Cl-ClO bond and completes that catalytic cycle. So in order to determine the rate at which ozone should be disappearing, if this is the mechanism, you can plot the concentration of ozone against calendar time, and here are the points observed by the aircraft. This black line is the rate for the CLO plus CLO alone. The dashed line is a combination of CLO plus bromine, putting in the Wofsy-McElroy combination. But the sum of those two simple rate-limiting steps exactly matched the rate at which the ozone was disappearing over the Antarctic. And that did it. The chemical community stepped in behind us and backed us completely against the ranting and raving of DuPont. And by the way, I don't know if you know this, but the op-ed page of the Wall Street Journal has made it clear that I abuse everybody I work for. I tell them what to think. I don't listen to them. I take money that I put in the form of gold into saddlebags, and I go to Mexico absconding with this. I mean, on and on. Every time I open because the Wall Street Journal, the core of it is research. The op-ed page is something to behold, and fortunately, it happened early enough to me that I've outgrown it. Okay, so this then was what pinned down the Vienna Convention and the subsequent London Convention on the protection of the ozone layer. And so I should also point out that doing the measurements in the Arctic had some important ramifications. First of all, the United States didn't sign the ultimate Montreal Protocol. They're almost the last nation to sign it. And it wasn't until we measured elevated CLO over northern Maine that Al Gore came out and said, well, now we have an ozone hole over Kennebunkport, which of course is the Bush's summer place. And that was actually very effective because within 2.5 weeks, the United States signed the Montreal Protocol. He really helped. He made the whole resistance to this look so stupid that he won the day, and we owe him a great debt of gratitude. But from a mechanistic point of view, and you can see the same anti-correlation that's true in the Arctic vortex as it is in the Antarctic, but the chemical kinetics turned out to be incredibly interesting and worrisome, because if I plot water against temperature, I have a regime shown here on the right where there's absolutely no conversion of inorganic chlorine to free radical form. And yet, if I cross this threshold, just 2 Kelvin difference, or half a part per million of water, moves you into a domain in which this is the dominant conversion. The heterogeneous catalytic conversion of inorganic chlorine to free radical form occurs extremely rapidly, but its onset changes by a couple orders of magnitude in just 2 or 3 Kelvin. It's one of the most remarkable systems. And the worrisome part is that over the central United States in the summer, we sit right here at the cusp. Okay, so this observation then of the chemical complexity when you're converting the inorganic chlorine to free radical form compared to non-conversion is dramatic, clear, and I have never seen a system in a chemical circumstance that comes close to this sensitivity. Okay, so then of course we had to go back rebuilding all of the instruments to fly on aircraft. Again, the research group, now incredibly capable not only of the science but also the engineering. And this is a thing that I learned as a graduate student working in and Charlie Barth's group, he had a very small cadre of extremely capable engineers working to build all these instruments that are going to Mars and Venus. And I didn't know it at the time, but it was the model by which real progress is made, because it's really the union of the scientific problem and the solution to that involves design, engineering, and so on that really progresses the situation. So we have many, many examples. Now, I want to pick out this picture in the middle because this represents a core of our kinetics group at the time, because we were pursuing a huge amount of effort in determining the reaction rate constants for all of these systems, which were coming into us faster than we could deal with them. And so these reaction dynamics, the rates of the reactions were established in the laboratory just up here one floor by using large flow systems that we could control a very large dynamic range in pressure and temperature, because these are all mixed molecularities. And so this is an example of the members who were working on the kinetics of this system. And so now I'm going to turn to the final piece here, which is the most shocking changes in global structure in human history. And I would put the Antarctic ozone hole up there as Exhibit A, but very close behind it is what's happening in the Arctic. This is the volume of floating ice in the Arctic in thousands of cubic kilometers. And in 1979, it was about 18,000 cubic kilometers. Within 40 years, it's dropped to 4,000 cubic kilometers. 80% of the volume of the floating Arctic ice has been lost in the last 40 years. And that's after 10,000 years of stability in which that Arctic ice volume was essentially invariant. That is a problem that is central to our concern now, because permanent rapid loss of Arctic floating ice, and also you can see that both the first and second derivatives are negative. So there's a very powerful feedback in the system that's driving the continued destruction of that. And the question, of course, then becomes, well, can we lose 80% of the volume of the Arctic ice and recover to a stable condition? And the answer is profoundly no, because now we get into this issue of feedbacks. And if I were to show you a diagram of this area 50 years ago, the entire area would be covered with snow and ice. And that means that warm air coming in from lower latitudes is cooled, because, of course, everything cools as the fourth power of the temperature. So the ability of atmospheric motion to carry heat into the Arctic was limited entirely by the presence of that cold background into which it was radiating. When we unblock both the Atlantic and the Pacific entry into the Arctic Ocean, it blocks the flow of warmer, low-latitude air, water into the Arctic. But when we lose that, we have free flow of warm water into the system. But of greatest importance is that once you lose that white background, instead of reflecting 95% of the radiation, you absorb 90% of it. And that feedback is what's driving the irreversibility of the system of losing Arctic ice. So the answer is profoundly no, and I bring it up because these feedbacks turn out to be working against us in many, many systems that I don't have time to cover. But what happens when the Arctic ice cap is lost? Well, the first thing is that, over actually millions of years, Greenland and the glacial system of Greenland was protected by that locked-in ice and snow of the Arctic. But when that's gone, Greenland is now exposed, and it carries with it 7 meters of sea level rise in that glacial system. And what happened starting in 1980, we have some radar observations. There was no surface melt on Greenland. Early 90s, surface melt started to cut in, and now every year the entire surface of Greenland is awash in melted water. But the problem is that that water doesn't just flow gently off the back of the structure of that glacier. It actually pours down through open moulins and delivers that water to the base that breaks the bond between the ice and the bedrock. And that's a profoundly irreversible feedback in the system. So let's just, for the fun of it, take a look. This is Cambridge. President Bacow had to leave because he had another introduction. This is really for him to see what happens when we start to add sea level. So let's add 3 meters. A good part of Alston goes under. Now, when we look back here, of course, this is Harvard, MIT is here. So the only good news is now that MIT goes under before Harvard. But I don't know if you can see any other, this is really worrisome. Gulf Coast, of course, Florida is famous this week because of the hurricane, but just a 3-meter addition to sea level takes out the entire southern part of the peninsula of Florida. So it brings us into this next question about what's happening to the rest of the melting Arctic. And this is methane clathrate. This is remarkable. It's an example of thermodynamics working at its best, because this is a cage of water and this is a methane molecule within it. And because nature is always driving toward greater entropy, greater disorganization, it's always trying to put a molecule into any vacuum it can find. But when you have organic breakdown, methane is the anaerobic production of that organic breakdown, and all of it goes into the ice structure, whether it's on land or whether it's on the bottom of the ocean. It's the same process. And so the storage of methane and CO2 in this is gigantic. And what's really worrisome is that if you look at the CO2 effective emission, because of course methane immediately is converted to CO2 on the timescales of decades, and you plot the effective CO2 emission against time up to 2015, this is the release from various scenarios for fossil fuel, but just 0.5% of the release of carbon in the upper 3 meters of the Arctic is equal to the total amount released by fossil fuels annually. And that means you can solve the problem of terminating CO2 and methane from fossil fuel combustion, which we definitely have to do. But this is thermodynamic irreversibility. This is going on independent of whether you terminate CO2 and methane from fossil fuels or not. And it's these feedbacks that are driving the system. And when you look at the way in which things are analyzed, and people say, well, we can solve this by terminating CO2 and methane from fossil fuel, you realize that from a thermodynamic point of view, that is complete nonsense. So this brings us into the next challenge, and that is, how do you measure the evolution of CO2 and methane coming out of the Arctic? And so now we shift to a very small plane that's flying just 10 meters over the surface, because we want to look at the anti-correlation of vertical fluctuation in velocity simultaneously measured with concentration, so we can measure directly what the flux is, both of methane and CO2 and its isotopes coming out of the Arctic. And this brings up a picture of John Langford and myself. John and I met 35 years ago, right after the Antarctic, wherein I was profoundly worried about sending pilots over the Antarctic because of how dangerous it was, and I realized that robotic aircraft are the only way to actually approach this problem. So serendipitously, a couple of weeks after I got back from the Antarctic, I got this letter from this completing PhD student at MIT in aeroastro, John Langford. And so John and I have been working together now for 40 years, and I'm going to talk about what the current project is. But John also supplied the aircraft for this particular NSF mission. And it also embodied a whole new connection to our physics friends, because this is a quantum cascade laser, Federico Capasso's QCL, which has revolutionized our ability to measure multiple interacting reactive species by using a cavity enhancement that expands a 30-centimeter cell into 3 kilometers of absorption length. So we can see all of these molecules with exquisite detail, and it's opened up a huge avenue into collaboration across the university. And so we have the carbon dioxide axis and the methane axis, and the key point here is this irreversibility. And George, I think this is your favorite variable, is it not? Gibbs free energy is the clarification variable that makes your life entirely understandable. All of your life. That's not very funny, I realize that. Okay, but the spontaneous flow of heat into these subsystems of the climate is simply a reflection of nature's drive for maximum disorganization, which is the benchmark of spontaneous change. And it's Gibbs free energy that really tells us how that actually functions. And it tells us something unequivocal, and that is you can't just expect that heat to flow out of the system. So this is not about temperature, this is about heat. And you can actually look at the way heat flows into these subsystems. It's almost like a cancer flowing into an organism. It's very difficult to identify, stop it, reverse it. And in particular, this energy circulating between the Earth's surface and the amount of energy required to melt that Arctic ice cap. What is that ratio? And this is one of those back-of-the-envelope calculations that is so upsetting, so revealing, and so important. And that is that you can take, of course, the simple expression for calculating the power emitted by any body. It's the area times Stefan Boltzmann, and it's the 4th power of the temperature. But that allows you to instantly, on the back of an envelope, calculate the energy per unit time emitted by the sun, the energy per unit time emitted by the Earth's surface, by the top of the atmosphere, by a human being. This equation works beautifully. But it also carries a profoundly worrisome aspect, because when you look at the trapping of infrared radiation within the atmospheric system, you realize you've got almost 2 times 10 to the 18 kilowatt hours of energy circulating just in the infrared. But then you think, well, I know that the ice is disappearing. How does that circulating infrared component compare with the energy per unit time to melt that ice? And this is the unfortunate, straightforward calculation, where if you calculate the circulating infrared and you divide it by the amount of energy required per year to melt the ice at that rate, that's a 50,000 to 1 ratio. A tiny leakage of infrared radiation poleward is all that's required to melt that Arctic ice cap. And the fact that we've had a climate that's been stable for millions of years is a miracle when you look at the sensitivity and the delicacy of this system. So now let's finish up by looking more broadly at what's happened. We've all realized in the last 2 years there's been this explosion of the realization of the impact of what climate is doing to the globe. There are calculations that come out all the time about the economic destabilization, but they're looking at cutting world economy by 23 trillion by 2050. And of course, it's the insurance industry and the financial industry that system that is profoundly aware of this and developing this. But if you just look at the data, these are the United States billion-dollar disaster events from 1980 to 2021. It's gone up now typically $500 billion a year just in the United States from climate-induced problems. And then this came out just yesterday, the ruinous floods and constant heat. We just read about this now every single week. And climate change, emerging threat to financial markets. This water supply question is going to be one of the biggest to emerge because the entirety of South America is fed by these delicate little glaciers in the Andes. They're disappearing very, very quickly, particularly during growing season. And the Tibetan glacial system that supplies 90% of the water to India, 75% to China, it's also extremely delicate because that glacial system is much smaller than what we see in the polar regions. And then finally, these drought systems, and of course, if we had time, we could talk about why is it drought and why is it severe storms, but it's the worst drought in the West for 12 centuries. And all of a sudden, just in the last 2 years, all of this is coming to bear. Smoke-filled summers, tipping points for remarkable changes in the structure. Again, the release of methane and CO2 from the Arctic is really the sleeping giant here. And until we solve exactly how to reverse that, we have a serious problem. Increasing wildfires, the way it impacts snowpack and wildfires, uncharted territories of destruction, as the UN chief has brought out. This is really remarkable because it wasn't forecast quantitatively. This came on us, we read about it now, but we didn't have any calculation of this 3 years ago about how quickly this would occur. So we don't have quantitative forecasts of risk. And so that's our challenge now. We need to come up with an entirely new system that's capable of establishing a quantitative calculation of risk from each one of these factors. And the issue here comes back to the same principle. Until within each one of these climate subsystems, you can simultaneously measure the coupled variables with high spatial resolution, you cannot determine the physics and chemistry driving that response. And so we need a new observing system. And there is a certain consistency here, right? We come up with a new problem, we have to have a way of observing it, and this is Exhibit A. And so we want to develop quantitative forecasts of the rate of sea level rise. We want to develop quantitative forecasts acre by acre of the probability of wildfires breaking out. And of course, this is famous throughout the West, but it's also true now of Asia and many other areas. So this priority of looking at how glaciers break up turns out to be a physics problem of incredible interest. And working with Dusty Schroeder at Stanford on this one, he's a world leader in ice-penetrating radar. And so in order to dissect what's actually occurring in a glacial system, you have to simultaneously measure the topography, the shape underneath, and the dynamic of what's going on, the flow velocities, the structures, and measuring each one of those variables simultaneously over time is a crucial part of diagnosing this. And so the advantages of operating a climate observatory from the stratosphere are remarkable because it's dynamically stable. It has no weather, so we want to drive these aircraft with solar-powered energy, but we want to depend on it. And we want a close proximity to the scientific target. And so, again, back to this working collaboration with John Langford, been working on these aircraft to solve this problem. And this is an aircraft, the newest version of which couples all of the new electrochemistry and guidance and control systems as well as materials. And the aircraft has a wingspan around 30 meters, but it has a flight duration of 12 months. It can fly in the stratosphere for a full year to altitudes of 85,000 feet, but it can carry instruments specific to the particular climate target. And so this, of course, involves the development of a whole new array of lasers, LIDARs, radars, and so on, and brings us full force into collaboration across this university because the instrumentation development is just as important as any other aspect of it. And it's really enriched our life and our experience. And so one of the biggest problems is the large-scale dynamical structure of the atmosphere. That controls almost every aspect of the climate, and yet the physics that's controlling this has never been diagnosed. And until we understand the physics controlling that large-scale overturning circulation, we can't possibly solve the problem. Okay, so to do that requires a whole set of instruments flown in situ with this aircraft that goes along with the simultaneous LiDAR radar measurements that can be made vertically. Now, this issue of convection over the United States, this is the only place in the world where the storm systems are strong enough to drive water vapor directly into the stratosphere. And the reason the United States is unique internationally is that the warm Gulf of Mexico supplies the fuel that drives the explosive vertical motion that then inserts water vapor directly into the stratosphere. And that's what converts inorganic chlorine to CLO, except this isn't over the Arctic and the Antarctic in the winter. This is over the central United States in July and August. So this is a central problem we're trying to address. And again, it's a matter of understanding ozone loss to a very few percent because of the extremely important medical connection to it. Now, in the last month, the National Academy of Sciences has published this critical review, this report, that for the first time says the entire strategic structure of the U.S. climate research program is flawed because it doesn't focus on risk. And the crucial aspect of calculating quantitatively what risk is from each one of these is the central objective. And so we had nothing to do with the authorship of this, but this turned out to be a profoundly important statement, finally, about the importance of quantitative risk. So now we're addressing this forecasting of hurricane structure, severe storms, wildfires, sea level rise, and so on, but using this new observatory built on the back of these aircraft. And of course, the economics and the climate change and intergenerational justice has been a very important statement about how critical this is. And again, this is back to our fundamental point that we have to measure those species, those variables simultaneously in order to dissect the physics and chemistry. So let's look at the federal structure that is dominating. And here we compare what the observatory from the stratosphere is compared to a satellite system. And first of all, satellites in low Earth orbit are 500 to 800 kilometers above the target. This observing system is 20 kilometers, and you lose a signal. It's a square of the distance between that target and the observer. So you gain a factor of 500 over 20 squared from that point of view. The satellite moves over the ground at 8,000 meters a second. This observatory moves over the ground at 30 meters a second. And that is a crucial aspect for gaining high spatial resolution. Next, we're operating below the ionosphere, which blocks large segments of the electromagnetic spectrum that we don't have to be worried about, but it eliminates large parts of satellite observations. And finally, the majority of these unsolved problems stem from confined geographic regions. When you think about it, Greenland is 0.5% of the area of the globe, and yet it's a dominant contributor to sea level rise. Western wildfires, 0.5% of the area, but they dominate the problem, and on and on. Every single one of these is highly limited in its spatial extent, and the result when you have a satellite in orbit is it spends much, much less than 0.5% of its time over the specific target. But with this observing system, not only do you spend 100% of the time over the target with the instruments designed to attack the problem, but you can guide the trajectory of that aircraft according to what the instruments see instantaneously. And that gives you another couple orders of magnitude gain. As I mentioned before, Norton Allen writes all of our algorithms, and he writes the ones connecting those instruments to the trajectory. So we're developing tested and trusted forecasts of risk. That's supplying the information to do that. And this engages directly the solar-powered stratospheric aircraft, which we're very excited about. And just to underpin this, last week was its first flight. Here it's coming in for a landing. This is Manassas, Virginia, and landing successfully. And the team that developed it, again, this is multi-university, multi-age group, but this was a tremendous step forward for this observatory, which we are inclined to call the Harvard Climate Observatory. And the other thing is that this engagement of Harvard faculty has been a profoundly important part of this. Cryospheric sea level rise, of course, but public policy, economics, robotics, analog, digital, nanoelectronics, optical mechanical design, biosphere-atmosphere interaction, geoengineering, quantum materials, applied math. All of these elements are connected and drawn in by this tremendous need for quantitatively settling once and for all how these systems operate quantitatively, and to then create a quantitative forecast of risk from that. But it takes a massively greater number of disciplines to actually accomplish that. So this is the Harvard Climate Observatory then. It's for the first time it's essential link to economics, policy, and risk. Now, the third most shocking change in global structure was this onset of the impacts of climate. And I think I am coming close to the end of my... Ted says, yes, you better, yeah. I expect you to say, no. All right. So I just want to end up by saying that one other thing that George mentioned was that we need to think very carefully about restructuring undergraduate education, particularly in the physical sciences at this university. And it was some 10 years ago that I started working with Greg Tusi and Lou Wang. We're now a threesome. And the idea was that we need to provide undergraduates in the physical sciences not a course that extracts them from the subject, but one that draws more and more students in, because in order to be a proactive member of society now, you have to have the fundamental knowledge in order to know how to function. But it's also, when you look at the life sciences, they took biology and chemical structure and molecularity, and they created the life sciences that not only became intellectually extremely engaging, but it also delivered to society crucial insight into disease and all of the aspects that life sciences are now bringing to humanity. The physical sciences have tended not to be as responsive, let's put it gently. And this gets back to this issue that I mentioned before, where I started out with 330 physics concentrators, 19 of us finished. And when you look at the data, that kind of fall off is not that unusual. But this has to be corrected. And what's remarkable is that when you join the aspects that are intrinsic to the physical sciences, they can address this problem, the problem of international technology, of climate, of power. And the result of this was, I said, okay, well, I'll just write a textbook for this course. Well, typically I misjudge the amount of work going into one of my research projects by a factor of 3. This one I misjudged by an order of magnitude. And my wife, Shireen, who's sitting up in the back, withstood destroyed evenings and weekends for years to work through this. But I'm committed now to the fact that our undergraduates are graduating. Well, the course has about 400 students in it now, but they graduate well informed about these critical aspects, and I think it's profoundly exciting to teach a course like this because their engagement and their intrinsic interest and their innate ability comes through in vibrant form, and that's one of the reasons that I have the loop blocked off in front of the econ department so they can drive we have a Tesla, and this is a racetrack, okay? And so spring term, Saturdays, they come in groups of 4, and by the end of term, about 250 have driven that electric car, and they've also tested its performance. And this is a very exciting thing to see, and it represents, I think, the recognition that the future is very exciting if we come to understand it, and if we guide society correctly. It's the most exhilarating, challenging time to be 20 years old in the history of the arc of humanity, and I think that's a message we want to deliver. And again, I would just end by thanking the Dreyfus Foundation profoundly for this, and also thanking my colleagues with whom I work every day. Thank you. Well, thank you for that. Thank you.
I think we have a few minutes for Professor Anderson to entertain a few questions.
It's Jim Anderson, by the way.
Professor Anderson would be happy to entertain any questions from the audience.
No, I never correct him twice because he's so big and strong, he just, I won't even try.
Going once.
Yes.
Can you give us some idea about the anatomy of the instruments, like how you're monitoring, for example, with the free radicals?
Yeah, oh, good question. So the question is, what's the anatomy of one of these instruments that, for example, measures free radicals? That's a really great question. And I actually have 30 slides of that. And that was going to be the next thing I discussed, but I was looking at the clock and I thought, no, Ted's...
It's your party, Jim.
Yeah, that's what he says, but I knew that. Okay, so let me answer the question this way, because the question is really an outstanding one, and that is that in order to measure a molecular entity at the 10 to the minus 12, 10 to the minus 14 level, you have to depend on the fact that if you promote an electron in that molecule, it will reside in the upper electronic state, and if it jumps back to the ground state and re-emits that photon, then you can use that photon emitted at 90 degrees from a beam of photons that resonate with that electronic transition. So there's a fundamental design geometry that has a laser, or whatever the source is. It has a flow going through it, and it has an observation 90 degrees from that to capture that tiny fraction of radiation resonant with that electronic transition. And by using that and developing increasingly powerful sources and so on, that's how you get to a part in 10 to the 14. And now there are, I gave you a glimpse of what the long path absorption looks like. where we use Federico's quantum cascade laser, and we scan through it, but we can expand that path length from 30 centimeters to 3 kilometers. That gives us much greater sensitivity. So that's a brief answer to your good question. Yes?
Is there a phenomenon of interest you're trying to find the solar power?
Sorry?
Is there a phenomenon of interest specifically you're trying to find with the solar power probe, these first trials?
Is there a phenomenon of interest?
Maybe you're trying to find with the solar power probe.
Oh, you mean what are the first problems we're going to address? Okay, all right. Well, the first thing we're going to do is to use some of the in situ free radical measurements that we have, the core of which can be converted immediately to the aircraft. The larger developments are actually in LiDAR and radar systems. And this turns out to be an incredibly interesting aspect of the research right now, is developing greater and greater power for LiDAR and radar systems, but also the intricacy of how you separate out the spectral signature coming back from those. So there's a huge amount of software development in that. But basically we're looking at developing quantitative approach to sea level rise, to wildfires, which we use radar to measure moisture in the upper 50 centimeters. It turns out to be very powerful for predicting. We can determine the trajectory of hurricane systems far more accurately than currently, because we can probe the core of the dynamics of the hurricane rather than just taking a picture of it. And so those are some of the areas that we're going to be looking at first. Okay.
All right. If there are no further questions, please join me in thanking Professor Anderson for a wonderful.
What a nice audience.
Thank you all for coming, and for the invited guests, please join us at the reception and thank the Dreyfus Foundation for sponsoring this wonderful event.
Thanks.